Okay, so we want to talk about torques and speed for different types of loads. Okay, so what we see here is that torques are for rotational structures like pulleys and motors. We're focusing in on motors rather than pulleys, but it's the same basic idea. And so if I have a linear force at a distance r right from the center of rotation, then I get this relationship between torque, which is a rotational force, and the linear force. So the bigger the radius is, the bigger the difference is between the torque and the linear force. So lots of times we're interested in velocities. Well, if I think about a rotating system, the velocity is basically the rotation or the speed that the circumference is traveling. So if I want to convert between linear speed and angular speed, I just multiply it times the radius of the rotating part of the system, where the rotation speed is equal to how many radians per second, or the change in the angle as a function of the time. So in order to do this, we want to talk about mechanical power. So mechanical power is going to be the torque times the rotational speed. Now, if we wanted a different torque and a different speed, but we can use a gear system. So a gear system can change the ratio of the radiuses, change the ratio of the speeds and the torque. So you can kind of see when you're looking out here that this small one looks like, if I'm looking at some point right on the outside, is going faster than this one. So I can increase the speed by, and that's going to correspond to dropping the torque, or vice versa. I can decrease the speed and increase the torque using a gear system. And the gears can be gears like this. It could be multiple gears. It could be belts, different ways to do this type of gearing system. So now let's talk about what we're doing with our motors, and this is going to be talking about these loads. So there's two main types of loads that we're going to be focusing on. One is a constant torque, and one is a quadratic torque. So here are some examples of constant torque. So first of all, if I have a crane type system, so if I look right here, if I have like a pulley and then it's going down here and I have some load right here, this is going to have a fixed weight. So this is going to be constantly, even when this is being pulled up and down, the amount of force going down based on the weight is going to stay the same. So no matter how fast I'm going, the torque stays the same on the system. Similar with a lateral type system. So if I have a treadmill, the treadmill really has like a motor sitting here driving a belt around here. So now what's going to happen is the torque on this system is going to be related to like the friction. So the friction is going to have an opposing force against the rotation. So if this is my torque going this way and I have some friction on it, then that's going to be the same. So the amount of friction is independent of how fast it's going. So I have a constant torque independent of speed. Okay, so now let's look at quadratic torque. So with quadratic torque, if I'm displacing mass, or in most cases like air or water, the more that I'm displacing, the more torque that it's going to be. So if I have a fan and the fan is blowing, the faster the fan blows, the more torque it's going to put on the motor because it's moving more air. Same thing if I have a water system like this. Now, the car is kind of interesting because this is a friction one here. So the tire friction, that's going to be a constant. So that's going to be a constant torque. But right here, where you're basically getting this aerodynamic drag, this force right here is going to be a quadratic, because I am displacing the air. So the faster I go, the more torque it puts on the system. But the resistance of the tires doesn't depend on the speed. If I'm moving, it has one fixed speed. So let's look at these relationships with respect to a DC motor. So here is a constant, this is the speed along the bottom and then the torque going up. So if my load is a constant torque, you see my torque stays the same as I go along. Now my motor, if I have a DC motor at a fixed voltage, you see its torque speed relationship is like this. So it has high torque here and high speed here. And if I take and put this load, this constant torque load on this motor, I have to find the interaction, the coupling between the two, and that's going to be the speed that it operates at. So if I have a constant torque this way and my motor has this torque speed relationship, this is going to be the actual speed of the system. Now, if I want it to go faster or slower, you see I can change the voltage and change this plot, and then you can kind of see that I'm going to get different speeds as I do that. Now, if I go down to a quadratic relationship, you see that now this is my load. So my load is going to have a torque speed relationship that looks like this. So the faster I go, the more torque it is taking. And again, if my motor is a linear DC motor, so then you can kind of see it looks like this, and I get this speed. So I look at the cross between my load and my motor. And again, if I want to change the speed, I'm going to have to change my DC motor plot by changing its voltage or adding resistance in there in order to slide it across. And so that is how we're going to have the different types of loads and trying to figure out what the speeds are for a specific motor.